Most small galaxies may not have supermassive black holes at all. That is the core result. It directly challenges a long-standing assumption in astronomy. For decades, astronomers believed almost every galaxy hides a giant black hole in its center. New evidence from NASA Chandra suggests that belief often fails. In the next few minutes, we will follow the data step by step and see why galaxy size may decide whether a black hole ever formed. The result comes from a large observational study using NASA Chandra X-ray Observatory. Astronomers analyzed data from more than 1,600 galaxies. These galaxies were observed over more than 2 decades of the Chandra mission. The sample spans a wide range of galaxy masses. It includes systems much larger than the Milky Way and extends down to dwarf galaxies with only a few percent of its mass. The method relies on X-rays, not on seeing black holes directly. Black holes themselves emit no light, but when gas falls toward them, friction heats the gas. That hot material can glow brightly in X-rays. A compact bright X-ray source at a galaxy center is a strong indicator of a supermassive black hole. Using this principle, the team searched for central X-ray signatures across the entire galaxy sample. The contrast between large and small galaxies was striking. In massive galaxies, especially those comparable to the Milky Way, central X-ray sources are very common. The study concludes that more than 90% of massive galaxies host supermassive black holes. This confirms earlier expectations for large systems. Smaller galaxies behave very differently. In dwarf galaxies, only about 30% show evidence consistent with a central supermassive black hole. Most dwarfs lack clear X-ray emission from their cores. This absence is not random. It becomes pronounced below a key mass scale. Galaxies with stellar masses below about 3 billion times the mass of the Sun usually do not show bright central X-ray sources. This mass is comparable to that of the Large Magellanic Cloud. At this point, there are 2 possible explanations. One possibility is that dwarf galaxies do contain black holes, but those black holes are faint. Smaller black holes pull in less gas. Less gas means weaker X-ray emission. That emission could fall below Chandra sensitivity. The second possibility is more radical. Many dwarf galaxies may simply not have black holes at all. The researchers tested both explanations. They modeled how X-ray brightness should decline as black hole mass and gas supply decrease. As expected, smaller black holes should indeed be fainter. But the observations revealed something more. The drop in detected X-ray sources was steeper than faintness alone could explain. Even after accounting for weaker accretion, too many dwarf galaxies were missing central X-ray signals. This additional deficit points to a real decrease in how often dwarf galaxies host black holes. Elena Gallo, University of Michigan co-author, stated, "The analysis indicates there are genuinely fewer black holes in smaller galaxies. In other words, the missing X-rays are not just hidden signals. In many cases, there is likely nothing there to see." This finding has deep implications for how supermassive black holes form. Astronomers consider 2 main formation pathways. In one scenario, a massive cloud of gas collapses directly into a black hole. Such a black hole starts its life already weighing thousands of suns. In the other scenario, black holes begin small. They form when massive stars collapse, then grow slowly by accreting gas over cosmic time. If the second pathway dominated, dwarf galaxies should host black holes nearly as often as large galaxies. Small seeds would be common everywhere. Over time, some would grow and some would remain small, but the occupation fraction would be similar. The Chandra results do not show that pattern. Instead, the data support the first scenario. Direct collapse events are expected to be rare. They are more likely to occur in massive galaxies with deep gravitational wells and abundant gas. Fan Zhou, University of Michigan researcher, stated, "Getting an accurate black hole head count in small galaxies gives clues about how supermassive black holes are born. The low occupation fraction in dwarfs fits naturally with direct collapse occurring preferentially in massive systems." Anil Seth, University of Utah co-author, stated, "Formation of big black holes is expected to favor the most massive galaxies being formed." This interpretation explains both ends of the observed trend. Massive galaxies almost always host black holes. Many small galaxies never formed one. The consequences extend beyond galaxy evolution. If dwarf galaxies often lack black holes, then black hole mergers should be rarer than previously expected. When dwarf galaxies collide, there may be no black holes to merge. This reduces the predicted number of gravitational wave sources detectable by future observatories, such as the Laser Interferometer Space Antenna. It also means fewer stars will be torn apart by black holes in dwarf galaxies. Thank you for being with us. Please subscribe, share, and like. Taken together, the Chandra results suggest that the Milky Way is not a universal template. Some galaxies may have grown and evolved without ever hosting a central supermassive black hole. The universe may be less crowded with black holes than we once believed, and galaxy mass appears to play a decisive role in determining who gets one and who does not. Thank you for being with us. Please subscribe, share, and like.